So for fission, they don't really have any formulas. I imagine they're going to have you do this, right? Really, what it is it's going to be the parent nuclei, right? So you have a neutron, right? And then it's going to hit a parent nucleus, right? And then what's going to happen here is you're going to get, it's going to split, right? Because fission means to create fissures, right? We're splitting this thing apart, right? Okay, you're going to split this guy apart, right? But you're also going to release some neutrons, not just the neutron that came in, right? But you're also going to have these spare neutrons, right? So typically, when I see these on the IB test, what they do is they give you this, and then basically you have to balance the nuclear reaction. So you can look up the neutrons, the protons, and the neutrons of this, right? And you can look up the protons and the neutrons of this, right? And then just keep track of your neutrons, okay? The protons here, these guys are always going to add up to the protons of this guy, right? But the neutrons are going to be less. And the reason is that lighter elements require fewer neutrons to bind them together. The heavier ones have excess neutrons, and because there's an inherent instability for larger nuclei, right? Because the strong nuclear force is very short range, and so large nuclei are not held together very well, right? And so keep track of the neutrons. This particle A is going to have so many neutrons. This one's going to have so many neutrons, right? And then you're going to figure out, oh, hey, it's releasing a whole bunch of these other little guys, right? And of course, that's how you can set up a fission chain reaction, right? In nuclear reactors or in an atomic bomb where you're trying to make it happen all at once, right? These guys go on um, to cause more reactions, right? Now, the funny thing about neutrons is that if the neutron's going too fast, it'll actually just go right through the nucleus because these big nuclei are just barely held together. It won't stick to it. It'll just sort of go flying through it, right? And it won't interact with it. So you actually have to slow these neutrons down. You have to moderate them, right? And if you want to be safe, you can use water to moderate them. If you want to be a little more risky, you can use graphite to moderate these. This is what they did in Chernobyl. And the only problem is that graphite burns, right? It's like high grade coal, right? It's just pure carbon. Um, and that's what happened in Chernobyl. They got it too hot and they lit the moderator on fire. And yeah, there you go. It almost sounds like an IB term, right? But anyway, so that's what it. And then when you do these equations, what you're going to do is you're going to look at this mass, right? The initial mass, and you're going to look at the final mass, right? Initial mass minus final mass is going to give you some change in mass, right? And then you're just going to, literally you could plug that in here and you can get the energy in joules. Nobody does that. You're just going to go multiply by 931.5 and you're going to get the energy per reaction. And these reactions give off on the order of 200, the 180 is a typical MeV, right? So just one atom gives off this much energy. Keep in mind that chemical reactions give off tens of electron volts, not million electron volts, but just like tens of electron volts. It's like TNT and conventional explosives, right? One atom gives off 200 million electron volts, right? So and the physicists saw this. Of course, that's the famous letter from Einstein to President Roosevelt, right? Is hey, there's this thing we discovered, right? We think that it's possible that a bomb could be made out of this, right? But anyway, that's the thing to look for. So they're going to give you something. It's going to break into a couple things. You've got to figure out how many neutrons are produced. Then you got to look up all those masses, subtract, multiply by 931.5. That'll give you the energy given off, right? Or if you plug it into this, it'll give you the energy in joules. I don't know. I've seen both. I've seen them actually ask for both. So I think that's it.